Welcome to today's Explainer. We are setting out to build a powerful mental model for physical science. Instead of just memorizing random facts, we're going to build a rock-solid foundation. By the end of our time together, you'll know exactly how to describe motion, track it on a graph, and explain how forces interact to cause changes in the world around us. Let's dive right in. Here is our roadmap for today. We'll start with motion and frames, move into graphing motion, and then explore force and inertia. After that, we'll do some cart practice to apply the math, look closely at interaction pairs, and finally finish up with a recap and a transfer question. All right, part 1, motion and frames. Where are we? Before we can describe movement, we have to establish a starting point. To define motion, we first need a reference frame. So what is a reference frame? It's simply a coordinate system from which motion is viewed and measured. Think about it. If you're sitting on a train cruising at 50 miles per hour, the book sitting on the table right in front of you isn't moving from your reference frame. But to someone standing outside on the platform, that book is flying by at 50 miles per hour. You just cannot accurately describe motion without first explicitly stating the background coordinate system, your reference frame, that you're measuring from. Now, there's a subtle but really critical difference in how we measure that motion. Speed is just a magnitude, an amount, like 5 meters per second. But velocity? Velocity is 5 meters per second east. Velocity absolutely must include a specific direction. If you don't know the direction, you only know the speed. When we're tracking movement in physics, we almost always care about velocity because the direction an object is heading completely changes the outcome of its path. Let's move to section 2, graphing motion, tracking velocity and acceleration over time. Let's track an object over 4 seconds, noting the time, velocity, and acceleration. Notice the exact moments in this journey. For the first 2 seconds, the velocity stays completely locked at 5 meters per second. The acceleration is 0. But then, look what happens at seconds 3 and 4. The velocity actually starts climbing. It jumps to 7 and then up to 9 meters per second, with an acceleration of 2 meters per second squared. Okay, it's time for our first quick check for understanding. Based on those numbers we just talked about, which part of the data shows constant velocity and which part shows acceleration? And most importantly, what is the exact evidence that supports your choice? Take a quick second to lock in your answer. Let's see how you did. The evidence is all in the rate of change. For constant velocity, we're looking at seconds 1 to 2 because the velocity stays perfectly steady at 5 meters per second. The rate is unchanging. For acceleration, it's seconds 3 to 4. The evidence there is that the velocity is actively increasing by 2 meters per second every single second. Acceleration is simply the measurement of how much that velocity is changing over time. Section 3, force and inertia. We've described motion. Now let's talk about the cause of change. This brings us right to the definition of force. In physics, a force is an interaction between two objects, measured in newtons. I want to pause here for a second because this is a massive point of confusion. Force is not a property an object contains. An object doesn't have force or carry force around with it. A moving baseball doesn't contain force. A force only exists as an interaction, a push or a pull occurring between objects at a specific moment in time. Since objects don't carry force, they rely on something called inertia, which is summed up perfectly in Newton's first law. An object is going to maintain its current state of motion, whether that means sitting totally still or cruising along at a constant velocity, unless it's acted upon by an unbalanced net force. If the net force on an object is 0, its velocity doesn't change. It is only when the forces become unbalanced that an object will actually accelerate or decelerate. Moving to section 4, cart practice. Let's apply the math and see how this actually works. Let's run through a practical example with a cart on a track. Before a push, our cart has a mass of 10 kilograms. The net force is 0 newtons, so predictably the acceleration is 0 meters per second squared. It's coasting along at a constant state. Now consider the cart after an unbalanced push. The mass is still 10 kilograms, but now there's an unbalanced net force of 20 newtons applied to the right. The resulting acceleration? 2 meters per second squared to the right. The arithmetic is incredibly straightforward. 20 newtons divided by 10 kilograms equals an acceleration of 2 meters per second squared. That cart example is Newton's second law in a nutshell. Acceleration depends entirely on 2 factors: the net force applied to the object and the mass of the object itself. A larger unbalanced force gives you more acceleration, while a larger mass actively resists acceleration. And that ties right back to the concept of inertia we just discussed. Section 5. Interaction pairs. Let's look at the symmetry in forces.
Time for our second check for understanding, and this one's a two-parter. First, based on that cart example, if the net force increases on the exact same mass, what happens to the acceleration? Second, and this is a bit of a preview, how does Newton's third law of interaction pairs actually differ from a simple pair of balanced forces?
Let's tackle part 1. If the net force increases on a constant mass, the acceleration increases proportionally. If we had pushed that 10-kilogram cart with 40 newtons instead of 20, the acceleration would just double to 4 meters per second squared. Makes sense, right? Now let's look at the second part of the question, which honestly trips up a lot of people. Let's clear up this common confusion. Picture balanced forces first. This is when you have two equal and opposite forces acting on one single mass. Imagine two people pushing on opposite sides of the exact same box. The net force is 0, so the box goes nowhere. Contrast that with a Newton's third law pair. This involves forces acting on two different interacting masses. If you push on a wall, that's one force acting on the wall. The wall pushing back on your hands is the second force acting on you. Two forces, two different objects. That is an interaction pair. And finally, Section 6, Recap and Transfer, bringing it all together. We've covered a ton of ground, so let's lock it in with 3 key takeaways. 1. Describing motion requires a specific reference frame. 2. Unbalanced forces produce changes in motion, known as acceleration. And 3. Forces are always interactions between objects, never a property an object contains. If you can keep these 3 facts in your head, you have absolutely mastered the foundational concepts for this topic. I want to leave you with one final provocative thought to test your new mental model. Imagine you're coasting on a skateboard and you push forward on a heavy brick wall. Using everything we just covered about Newton's third law and interaction pairs, identify the specific forces in that interaction pair and predict what's going to happen to your resulting motion. Think carefully about where the forces are being applied and which object actually has the ability to accelerate. Thanks for joining me for this explanation, and keep questioning the physics of the world around you.